Hello everyone, I'm Zuxin. I'm happy to present our new paper, Improving Perception via Sensor Placement, Designing Multi-LiDAR Systems for Autonomous Vehicles. I will introduce our paper from the following perspective. So first is the motivation. LiDAR sensors are becoming the critical 3D sensors of autonomous vehicles. The point cloud data generated from LiDARs has been used to perform a series of perception tasks, such as object detection and tracking, just as the figure shows. Unlike the RGB image data from camera sensors, point cloud data is irregular and sparse, which brings a lot of challenges for the downstream perception tasks. And since one LiDAR may not be able to provide a complete sensing capability for the autonomous vehicle, many self-driving companies may install multiple LiDAR sensors on their cars. However, since LiDAR is an expensive sensor, it may introduce much more deployment cost if we install too many LiDARs. So how to choose the number of LiDARs and how to optimize the utility of each LiDAR are important topics to study. Here is the general LiDAR point cloud-based perception pipeline for many real-world autonomous vehicle applications. First, we install LiDAR sensors on vehicle and collect raw point cloud data from the environment. Then we have to annotate those point cloud data and train the perception model. So how to improve the perception performance? The focus of most existing research is within this box. For example, people may develop some data augmentation methods or automate the data annotation tools. People may also focus on developing novel model architectures or some fancy training tricks to improve the perception performance. However, most of them are evaluated on a static point cloud dataset, which is collected in advance with fixed LiDAR configurations and environment scenarios. So they will not consider how the point cloud data are generated and what is the data quality. But as we can see in the figure, the sensing part is also a necessary and important part for real-world deployment. And as we all know, the data quality may affect the machine learning model a lot. So in this paper, we focus on data collection part and study how does the LiDAR configuration affect the sensing data quality and influence the final perception performance. In particular, the LiDAR configuration in this paper refers to the number of LiDARs and the location and orientation of each LiDAR on the autonomous vehicle. We want to address the two major problems. First, does LiDAR configuration influence the perception performance? And if the answer is yes, how to optimize the LiDAR configuration to improve the perception performance? Unlike many existing methods that focus on developing fancy machine learning algorithms to get some improvement on static datasets, we will focus on the data collection and the data quality perspective. To maximize perception capability, an intuitive measure is to collect as much information as possible given a budget of LiDARs. So we propose an information theoretical measure to represent the perception capability of a LiDAR configuration. A key insight here is that autonomous vehicles are deployed in different cities, so they encounter various conditions, including but not limited to road infrastructures and traffic patterns. So we aim to optimize LiDAR placement such that the lasers can focus on the important areas around the autonomous vehicle based on the customized datasets on different cities or different scenarios. To this end, we propose to model the region of interest, which is represented by a collection of small cubes, as probabilistic occupancy grid by calculating the probability of each cube to be occupied. The grid is created by registering information about the 3D bounding box positions of objects of interest, such as cars and pedestrians. And after we get the probability of each cube to be occupied, we can calculate the entropy of the probabilistic occupancy grid. And the surrogate cost function that we want to minimize is the negative entropy. The intuition is that we want our LiDAR beams to go through those areas with high occupancy probability as much as possible. For the experiment, we developed an automated data extraction framework in Color Simulator, and we use Scenario Runner to fix all the environmental variables, such as the vehicle movements and the pedestrian movements. We adapt the dataset to the Kitty format so that we can use many existing advanced detection algorithms to train on our dataset. Here are some experimental results. We use several baseline LiDAR configurations, which are all inspired by some self-driving companies. And the final perception performance is shown in the table. We can see that different LiDAR placement can indeed influence the perception performance. And the final row shows the perception performance of the optimized LiDAR placement. We can see our optimal LiDAR placement can indeed improve the perception performance a lot. And this is the visualization of the point cloud of a car in the same scene for different LiDAR configurations. We can see that our optimized LiDAR configuration can provide a dense point cloud on the car. And this figure shows the relationship between the proposed surrogate cost function and the perception performance. We can see that minimizing the surrogate cost can improve the perception performance. And here we list some applications of our methods, and more details about those applications could be found in our paper. And here are some takeaway messages. We show that LiDAR configuration will indeed affect perception performance, and we can optimize the LiDAR configuration by our surrogate cost function to improve the perception performance. And thanks for your listening.